So before we actually start with today's material, I just wanted to quickly touch on a few points from yesterday. The first thing is that obviously, as we were talking a little bit yesterday, the sort of debate of R versus Python came up a little bit, and just so that I could follow up and give other people's opinions and not just my own, I did a little digging today just to see what other data scientists and other programmers had to say, and I sort of tried to compile all this into one table. I thought the quotes at the top were fairly representative, was that if you are really strictly only doing statistics, R really might be the go-to programming language for you. If you're gonna have to do statistics plus something else, be that be writing algorithms or working with servers or trying to get everything online, Python might be a little bit more flexible and a little bit more easy to use. So it's definitely great to have both in your repertoire. But anyways, I thought this was at least a nice summary. And the good news is that you, actually, as we'll finally touch on at the end of today's topics, you really don't necessarily have to choose one versus the other. There's lots of ways to make them work with each other. The other thing that came up yesterday was that people didn't necessarily love the way that notebooks look, Jupyter notebooks look, which is totally fair. It's very different than RStudio. It's a very different look than MATLAB. One thing I wanted to say is that there are alternatives. I was talking about the Spyder installation for Python. This is what it looks like. It looks small, sorry, the text is small, but it looks a little bit more similar to things like RStudio. It looks a little bit more similar to MATLAB. Most importantly, you have a global workspace here, so if you wanted to keep track of your variables. Spyder's absolutely totally great program to use, and it comes already installed with the Anaconda distribution. The other thing I will touch upon and say is that there's a new thing that Jupyter is working on. It's going to be called Jupyter Lab as opposed to Jupyter Notebooks, where they are trying to make the actual core Jupyter stuff look a whole lot more like RStudio. So it's in development right now, and I was just playing around with it a little bit earlier today. It's pretty cool, but it still doesn't have like a global workspace feature. It's still missing some things, but that's actively on their to-do list, so keep an eye out for it if you wanted another Python equivalent of RStudio, so you're aware. The other thing, as we start moving into more and more content, I wanted to just make everybody aware on the GitHub page for this course. If you scroll down towards the bottom, there's a references section, and there's a lot of recommended textbooks and readings for how you can get more information. Obviously, this is a sort of short workshop that's only going to cover just the tip of the iceberg of learning Python. So again, go to that GitHub. There's tons of references. So for today's content, a lot of this was drawn for Python for econometrics, which has a really excellent pandas overview and statistics overview in Python. There's a lot of topics that was covered in there that we don't really have time to cover, like a lot of time series stuff, working with time data, dates, things like that. And I really regularly recommend going through that. It's also a huge compendium of tutorials for Python, and that's in the GitHub, so it's all documented for you. Okay. Switching over to the notebooks. First thing, this will probably just become a daily ritual, or at least a ritual for every time we meet. There have been some updates to the materials, because as I go through, I try to add some new things and modify some things. So if people want to go ahead and just download the latest copy, or if you just want to just save out the materials from Module 2, which is what we'll be covering tonight. The latest commit was 2 hours ago. And with that, while everybody's downloading, I'll just give you an overview of what we'll be covering tonight. Today is going to be hopefully more exciting. We're going to be moving out of core Python. We're going to be moving away from NumPy, and we're going to start getting into pandas, which is the funny named Python package for data frames, meaning that we're going to start really being able to actually load in and actually work and manipulate large data sets. We're going to do that first. I'm going to introduce the pandas library, its core content. We're going to start working with some data frames. After that, we're going to jump into visualization. So I'll show you guys some examples with the MATLAB plotting library in Python and with Seaborn, which is going to make visualizing data really quick and easy. And then we'll finish off tonight doing some statistics examples with SciPy and stats models. So, and then finally, at the end, I'll actually show you guys a few, or at least 1 or 2 examples of actually how to call R from Python. So that you can import things like LME4 and things like that, so you can actually run a lot of R models from Python.
I was ready to drill to send me the PowerPoint. deck real quick?
I will do. Oh, do you want me to send it to you right now?
Yeah.
Okay. I'm also going to send something to Megan right now.
And I'm going to send it to all of you.
Let's see what's in my email. Let's give it for the world to see. Let's ignore what's in my inbox, because you respect my privacy.
That was beautiful.
Thank you. All this and more if you continue taking this workshop. All right, let's do it. Okay, so we're going to open up tonight with the Pandas library. So like I said, this is going to be the library that's going to allow us to use data frames in Python, and it's going to recreate a lot of the same functionality that R has in terms of data frames, and it's going to expand on it pretty dramatically, I would say. So we'll skip all that intro. If you want to go read all the information about the development of Pandas, you can go to their documentation page. The other thing I've tried to do in all these notebooks is that if you see hyperlinks, I'm linking back to the actual documentation pages for all these software packages so that you can go and learn more and read more. Okay. To start off, in the Pandas library, there's going to be two main classes. In the same way that yesterday, the main classes of Python were strings and floats and all that, there's going to be two main classes in Pandas. Those are going to be the series object and the data frame object. The data frame object is going to be made up of a bunch of series, so we're just going to start with series, and then we'll move into data frames. Importantly, when I'm loading stuff from Python, you'll notice this line of code right here. There it goes. I'm not going to load the entire Pandas library. This is a nice function in Python. You can load in selective functions from a library. So from the Pandas library, I'm importing the series function and this one other thing. But to show you what a basic series looks like, I'm going to make this list here. I'm going to pass it into series, and here's what I get out. Not so exciting. It's the same list I put in. The only difference now is that it actually has an index. This is going to start becoming really important, because a series is essentially like a hybrid between a NumPy array and a Python dictionary. And that's because when we initialize a series, we can store it with a bunch of indices. So if you don't want the indices to be 0 through 5, you can instead give it letter indices, for example. And once it has indices, so again, just to be clear, we gave it these indices, right? The first 6 letters of the English alphabet. Once you give it, you can initialize a series from a list or an array, or you can initialize it from a dictionary. The only difference is when you initialize it from a dictionary, it's going to automatically interpret all of the fields of that dictionary, or all the keys from that dictionary, as its indices, as you can see. And that makes a lot of sense, because as we start going through series objects, it's going to function very much like arrays and dictionaries. So for example, we can do dictionary-like behavior by doing lookups. So we can look up the index D, and it'll return the value for that. We can do multiple indexing in the same way that you would do for lists or NumPy arrays. So we're going to take out the 2nd and 5th elements here from the series. So we get the B and E values. And you can also do slicing. Series are also very much like NumPy arrays in the sense that you can do, you can apply things across all the elements. So for example, we can add +5, or we can do comparisons over it, so we can see which of these values are greater than 0.5, and we can use those conditionals to index into a series. So if we wanted all the elements of the series that were greater than 0.5, we can search for that with this conditional, throw it in the brackets, put it next to the original series, and just get out everything that was greater than 0.5. So again, this should be at least vaguely familiar from yesterday, because series, again, just has a lot of the same syntax, a lot of the same functionalities we saw from NumPy arrays, and that's because they are just expansions of the NumPy array. It's a NumPy array plus these indices that allow you to do lookup. And further proof of this is that you can actually use the asMatrix attribute of series and just immediately convert it right back into its underlying NumPy array. And here we are getting it out. But because it's also like a dictionary, you can extract out the values. So here we're just extracting out the values. Here you can extract out the index. And in that same way, if you wanted to update the index from its alphabetic characters to something more descriptive, like index 1, index 2, and onwards, you can use the .index attribute to update the index. This is going to be true for series and for data frames, which is why I'm showing this So let's talk about operations on multiple series. So with NumPy arrays, we could just multiply everything together, right? So as long as the arrays were at the same length, we could just do element-wise multiplication or division. That's not quite going to be the case with series, because remember, they have indices, so they're specifically, oh, do you have a question? Or, oh, never mind. So what's going to happen is two series are going to match on their indices, because when you do an operation across two series, they're going to look and see whether or not they have the same index. So here we're going to make two series objects, or three series objects. We're going to do one that's going to have I1 through I3, another one that has I1 through I3, and a third one that has I3 through I5. So when we multiply series 1 and series 2, which again are just the same exact series, you can see they multiply out fine because they're matching on I1 through I3. But when we multiply series 1 and series 3, which didn't have matching indices, you can see what's returned is a new series that has missing data. And that's because anything where it's not matching on the index, it's not going to try to combine them even if they're of the same length. It's going to just fill it in with missing data. This is going to become really important for data frames when you start doing things like merging and joining, because you don't want to inappropriately combine different variables. As you all are aware, it's a big problem. And because series are just like dictionaries, you can do the same sort of insertion. So if we wanted to add a new value into a new index, it's the same exact syntax as we saw yesterday with dictionaries. So if we wanted to make an 8th index, do I7, and you just store it as whatever value you want. So here we're storing it as 5. Okay. So series, sort of like a hybrid NumPy array and a Python dictionary, where the lookup table becomes really, really important for those series functions. Does that make sense to everybody? It'll get much more interesting in about 10 minutes. I'm going to try to get through the sort of basic stuff as fast as possible, but please stop me if I'm going too fast. Okay, so let's just talk about some attributes of series, because just like yesterday when we saw that the minute we switched from Python lists to NumPy arrays, we gained a lot more, many more attributes. The same thing is going to be true now with going from arrays to series. We're going to gain even more attributes and even more functions that you can use to analyze your data. So let's just make a random new series here. We're going to give it this list of just a few floats and some missing data, the numpy.nin. I should say, whenever you see an NaN in your data, what you're looking at is the specific NumPy class. It's NumPy NaN, it's like an R NaN, just means no value, you're missing that value. We're gonna make this new series. We're gonna give it its indices, we're gonna give it its values, great. Let's talk about some of the attributes that you have. So in addition to doing pure lookup by, for example, doing, so I just showed you before, if we want to do one lookup, you could just put in the brackets and its field. We can do another lookup by using the .loc or location attribute. It's a little less important for series, but I want to introduce you to now because it's going to become really important for data frames in just a minute. If you wanted to look up a value not by its associated key or field or index, you could look it up by its index position, which is the iloc attribute. If you want to print out the first few elements of a series, you can use head. If you want to print out the last few elements of a series, you can use tail. Isnull is really nice, this attribute, because it's going to look through your series and find any case of NaNs. So here we had one NaN in the C index, and great, it's finding that for us. We also have, oh, yeah.
So the reason we're doing series, period, and the function is because our object is named series?
Yes, in this case the object, so that's a really good point.
So if I name the object like cat, I would just do cat.
You would just do cat.
Head or whatever?
Mm-hmm.
Okay.
So you're right, that's actually a really good point. I was doing that for convenience's sake. But if you look, the actual series function that you're using to make a series object is different in the sense that it actually has a capital S. So if you store this in a new variable, capital S series, you'd actually overwrite the function with the new variable. Yeah, exactly right. Exactly right. It's a good point. So if I wanted to be a little bit more verbose, I could have named this variable example series, but because I'm lazy and I didn't want to write an example series about 100 times, I did not do so. But that is a really good clarifying point. Series also have the fill NA attribute. So if you want to just fill in all of your missing data, this attribute, you just give it whatever value you want to fill in your missing data with. So you can see we've replaced our NaN with a -1, which is sometimes used, or 99s, or whatever your preferred missing data value is. The drop NA attribute is really nice. It will just automatically clear out all of the NaNs from your data, but really importantly, look that it maintains your index. So our C index was the NaN. It's now gone, but it didn't change the index. So for example, if we had a series that was 0 through 10 and we were missing 3 because you dropped like the third element was an NaN and we dropped it, and then you skip from 2 to 4, that's a nice indicator to know that you actually have done something where you're now missing rows from your data. So something to watch out for. So name your series intelligently so you know how to, or your indices intelligently so you know how to interpret whether or not you're missing data.
Is the index still in the series and it's just not being printed, or is it actually gone?
No, it's totally gone.
It's gone.
So yeah, so it's, if we do, so okay, I've got that. So we can look it up. Oh, actually, it's still in there. Oh, it's because I didn't save it. Right, sorry. Let's actually make this now into example series. So one thing I should point out this entire time is all of these things are not in place operations. So if you do drop NA, it doesn't store it in itself. It's going to make a new variable, which is why it's printing out. And that's what just confused me. So let's make example series. Example series, when we print it out, should look exactly like what we just had above, right? There's no C, and we check the index. Again, there's no C, so it's completely gone. There's no history of it. There might be a history of it, for example, when we talk about categorical data later on, which is similar to the R, the way that R handles categorical data. We'll get there in a bit. But no, if you delete it, it's gone from this thing. So be careful if you're doing drop NA and you actually want to have a stored history of stuff. If you want to remove elements of a series, you can just drop by its index. So here we can just drop by B and D, and it's gone. And same function that we saw yesterday, unique, if you want to get all the unique values out. If you remember yesterday, I showed you guys the NumPy unique with the flag return counts is set equal to true. That's compressed. So that's a nice thing in NumPy if you want to, if you have a really long array, you want to find all its unique elements, and you want to find how often those elements actually occur, like the frequency of those elements. That's been compressed, so you don't have to write out this long line of code. You can use value counts, does the same exact thing. So we have 2 instances of 1 and 1 instance of 3.1 and so on and so forth. Yep.
So it's like tables in R?
Yes, yeah, I guess it's like the most simple table you could actually produce from a series or a data frame. That's right. Although you can save it actually as a new series where the values now become their indices. So yeah, meta series. And we also get nice attributes like the describe attribute, and this is going to apply for data frames and for series. So if you wanted just quick summary statistics across your series or across your data frame, you can just use describe and it'll just spit it all out for you. So you'll get your IQR, and you'll get your mean, and you'll get counts. So that's a nice thing. Finally, if you want to join multiple series, that's just the dot append attribute. And we're going to set ignore index as false here because we don't want it to overwrite the previous index. So you can see it just concatenates as on, and now we have multiple A's and multiple B's and multiple C's and so on and so forth. Okay, those are series. I will say, in my experience, I have used series maybe 1% of the time I've imported pandas. They're not like most data you'll be using, because obviously most data you'll be using will be tabular and will actually be matrix data in the sense that we'll have multiple dimensions because we'll be looking at multiple variables. Just want to show you guys this because series objects are essentially what a data frame is in Python. It's just multiple series combined into a more useful data frame. You might not ever use these, but just be aware that they're there. More excitingly, let's get into data frames. This is exactly like an R data frame. It's going to have a lot of the same attributes that we just went through. It's just going to have the ability to do it across either rows or columns, as you guys will see. So again, I'm not importing the entire pandas package because it's quite large and there's a lot of functions in there that you probably will never use. So instead, I'm just importing the data frame function out from pandas. And what I'm going to do is, because remember, a data frame is going to be, at least in the starting example, it's going to be an actual matrix. It's going to be two-dimensional. We learned yesterday that we could make a matrix by storing a nested list or lists of lists, or a list of lists. I'm going to pass said list of lists into the data frame object, and I'm going to now give it this new flag, columns, because I actually want to name the columns of my data frame. Otherwise, it'll just give it 0, 1. So we have the most basic data frame, Foxtrot and Yankee as my columns. Just like series, I can initialize data frames from dictionaries. So for example, I can go ahead and just make a dictionary where I have the keys or fields Foxtrot and Yankee, and I can assign them lists. And the data frame function knows how to immediately interpret that and put that immediately into a data frame. This might start becoming more important and interesting later on when we get to web scraping, for example, because a lot of Python packages, when you're doing either API calls or you're doing certain web scraping, they will return dictionaries where different elements of a web page or different elements of an API call will be stored as key value pairs. So like the HTTP address or the username or so on and so forth. Because data frames accept dictionaries in this way, you can actually just pass those immediately from whatever your API call is or your web scraping call is into pandas, and then immediately have well-formatted, nice tabular data. So we'll get to that next week, but just as ahead of time, it's actually really nice that it can read dictionaries. It makes life nice and easy. In the same way as before that we could give an index, you can specify both columns and indices in data frames. So if you didn't want your data frame, its index to be 0 through however many rows you have, you can give it specific indices. That might be important if, for example, you wanted your indices to represent your subject's name or a specific date or a specific company or something, because then you can specifically do lookup by that company or whatever your data is comprised of. So the other thing is that what I'm showing here is that if there are incomplete values, these are actually the series that we defined all the way up above. So if the series indices aren't matching up, if you pass those into a data frame, it will keep all of the missing data. So like we saw before, we had these indices, and the third series, S3, didn't have the same fields as the other two. So when you put them all together, again, it's the same exact function as with series. When you join everything together, it's just going to fill in missing data with NANs. It's not going to try to merge them in weird ways. It's going to just return to you whatever you put into it exactly. So just be aware that if you don't have the same fields, if you don't have the same column names, it's going to return to you a lot of NANs. So it's not going to try to overwrite or merge your data under the hood in weird ways. It's going to be very explicit with how it's combining your data. Okay. So that's the basics of generating data frames. Is that clear so far, how to make them? You can initialize them from a list of lists, from a series of series, or a list of series, or from dictionaries. Cool with everybody? Okay. All right, let's just learn how to actually work with data frames real fast. So again, look them up. You can do lookup in the same way that you can do in R. So if you do the brackets and you apply them to a data frame, it's going to specifically be looking for that column variable. This is different than the series before when it was looking up by index. It's now going to look, so data frames are different than series in the sense that series do index lookup, data frames do column lookup, which is typically how you'll be using your data frame. The other nice thing is that data frames, or the columns of your data frames become new attributes of the data frame. So if you don't want to type out the brackets in the string, you can just call df.foxtrot, totally equivalent. Be aware that if you have, for example, columns that have that are like strings, like date and time, which has spaces in it, this feature will no longer be useful for you because you'll then have spaces. You'll have blank spaces in your column names. Yes.
If I wanted to just look up one specific row, I just do df, I don't know, say it's I5, just dot I5.
We'll get right there.
Okay.
That's a great question. So the other thing you can do is you can do multiple column lookup, right? You should obviously have that. And the other new attribute that you get with data frames is the columns attribute. So, of course, dot columns will return to you all your column names, but that's useful because, for example, if I wanted to return every other variable in my data frame, I could slice, in the way that we learned yesterday, into my dot columns attribute. So df.columns is returning my column names right here. I can slice into that, just like we did yesterday. So I'm doing the : : 2, meaning that I want to return every other element from this list. So every other element starting from the beginning would be Foxtrot and Yankee. So that's what's happening inside these brackets. And that's exactly what I get out when I'm indexing that into this data frame. I'm only getting these two columns out. So be aware that there's multiple ways of doing column lookup with data frames. Getting to the previous question, if you want to index by index, or the index, you use the .loc command, or the attribute, which is exactly as we saw before. So if I wanted to get I1, so I would do .loc I1, and you can get out that row. And it'll return all the columns for that row. If you do slicing on a data frame, which Python allows, or Pandas allows, you're going to slice down by row, you're not going to slice by columns. So if you wanted to slice by columns and get the first 3 columns, you have to do df.columns like that. But if you just give it the slice 3, it'll interpret it as slicing down the rows. So just be aware that some syntaxes or some syntactics work for columns and others only work for indices, or extracting out rows. The other nice thing about the .loc attribute is that if you wanted to get specific rows and specific columns, that's now possible with data frames. So the first field, or the first element, will be whatever you're looking up for rows. So here we're looking up the first 3 rows. And here I'm saying return to me these 2 columns. One final weird piece of syntax is that the slice operator no longer works here. This will error out. This will error out, even though it would work previously. But this is how you would want to do lookup with the loc attribute, specifying both the index and the column. That's probably the weirdest syntax with data frames. Did that make sense to everybody? That was okay? Cool. I can do the same sort of conditional lookup that we're doing with series, but applied specifically to columns. So for example, let's say I wanted to return all the rows where the Yankee variable was greater than 0.5. I can put the conditional for whatever elements in Yankee that are greater than 0.5, I can put that inside brackets and then index into my data frame, and it'll return to me all of the rows where Yankee is greater than 0.5. So that's another way to index through conditionally and get the rows out of your data frame that you want. This is just making it clear that you can get both your columns and your index out with the data frame. And just to dispel the magic, if there is any magic with data frames, just like series were sort of fancy NumPy arrays, data frames are also just fancy NumPy matrices. So you can see you can easily convert a data frame with the as matrix attribute and strip away all the index information, all the column information, and just get it straight back into a NumPy matrix. So there's nothing super yeah.
What's like the pro and con of using NumPy versus Pandas?
I say you don't have to. It's really not an either or. It's actually really both, because Pandas builds off of NumPy. So I should explain, under the hood, the entire Pandas library is building off of NumPy. So like I said yesterday, NumPy is sort of the most essential Python library, in that basically all of the main Python libraries that are used for data analytics in one shape, way, or form build off of NumPy. So they're not really supposed to be exclusive or competing, they're complementary. There may be weird cases, for example, where you would want your data frame not actually as a data frame, but as an array. So let's say there's a weird case where you actually want to store everything and save everything out as a NumPy array using those MPY files I showed you yesterday. I can think of really weird corner cases where that might be okay, or like that might be something you want to do, especially if you're doing clustery things. But we'll talk about that another time. Those are weird corner cases. Most times and for most data analytic problems, you'll be keeping everything as a data frame. I just want you to be aware of that under the hood, it's just a NumPy matrix. So if you're comfortable with NumPy matrices, there's a few extra bells and whistles on top of a Pandas data frame, but that's the entire reason why Pandas data frames work, is because they're building off of NumPy. If there's also a weird case where you needed your data frame as a dictionary, you can also use the toDict attribute and just immediately convert it back into a dictionary. I've never had to do that. It's there if you need it. Okay, probably more importantly, because most of you guys won't probably be making data frames from scratch, instead you'll actually be reading in data from a CSV file or a tab separated file or from a SQL database. Let's actually show you guys how to do this. This is where things will start becoming more interesting, hopefully, to everybody. Now that we're kind of through the sort of core elements of Pandas. So like I said before, series and data frames. A lot of what we just went through is the syntax. Let's actually start applying it to real data. So with the module 2 files that we downloaded from GitHub, as opposed to yesterday where there was only notebooks, today, if you might have noticed, there's a few extra folders that got downloaded. They're full of tab-separated files, and that's because we're actually going to start working with real data today. So there's 2 data sets we're going to be working with. One of them, well, they're both psychology experiments, because that's my discipline. One of them is a gambling experiment. We'll talk a little bit more about that in a few minutes. The other one is a Stroop data set. Maybe you guys know the Stroop effect. It doesn't matter. We can talk about that later. But the point is we're going to actually start working with real data now. Pandas has a lot of really useful functions for reading in all sorts of different types of data. So for example, there's the read Excel function, the read CSV function, and the read table function. The read table can supplant these two in the sense that you can read in Excel files or CSV files with read table, but you'd have to specify a whole lot of extra flags in the read table. In fact, the docstring for read table is super duper long. So remember, we can look up docstrings with the question mark. As you can see, there's a lot of things you can do with read table. Read table is like your go-to solution if you've got a weird data set that you're pretty sure you should be able to read in. And you really want to invest the time in learning how to specify all the correct flags so that all of your data is read in properly. It can take some time. If you don't want to do that and you know that you already have a comma-separated value or you have an Excel file, you can use these two. Reading in tab-separated files, which we'll be doing, is also really easy with read table. The other thing I want to show you is that I'm also importing this new library here called OS, literally stands for operating system. This module is really, really useful for just specifying file paths. The reason why I'm using it here is because half you guys are using Windows machines and half you guys are using Mac machines. And the worst thing is that the separator for file paths changes between Windows and Mac. So if I actually spelled out a file path, it would break for half you guys if I decided to go with Mac, or for the other half you guys if I decided to go with Windows. OS solves that. And how does it solve that? Because if I do this os.path join, and let's say this was folder 1, and this was my file name, what it does is it figures out what your operating system is and puts in the right separator. So for Mac, that's the \. For Windows, that should be the /. Or maybe I'm getting that reversed. You guys can tell me if I'm totally wrong. But for the Windows users, if you do os.path.join and do this exact same thing, you'll see that it'll actually give you a /. So this is a nice thing if you're sharing code with people and you're not sure what OS they're going to be using, and you want to make sure that people aren't going to run into issues reading in files. The OS module, the OS library is really the right way to go. Is that point clear to everybody? I'm going to be using os.path.join like 1,000 more times before we get through the end of the workshop, so just wanted to make it really clear what that command is. Otherwise, what I'm doing here with read table, I'm specifying the path of the file, and I'm doing a relative path because hopefully you've, or rather this notebook should be able to point to the data. Let me know if it can. Should be able to. And the other thing I'm saying is here I'm saying that the separator file, or the separator of our new data set is the tab separator, which is the /t. That is, in string speak, that is how you denote a tab separation. Is that working for everybody? Is everybody able to actually open that data set, or are you getting errors? You run that cell. Everybody's good? Oh, beautiful. Yeah?
So like would R you like specify the entire like path to like a
Mhm.
folder. So
So-
how does it know to like go there?
I'm cheating here in the sense that Jupyter Notebooks will assume as a relative path that wherever that Jupyter Notebook is stored, so we stored it in the Module 2 folder, the default relative path will be the folder from which you open that Jupyter Notebook. And the beautiful thing about GitHub is the way that I stored everything is that all of the folders containing all of the data are stored in the Module 2 folder. So if you open up that notebook from Module 2, it should be able to point to other things inside the Module 2 folder. So that's how the relative paths work. So that's why you don't have to specify it. If you moved the notebook, the Module 2 nodes file outside of that folder and then run this code, it will break because you've changed the relative path. If that makes sense to everybody. Yeah?
Can you define a different path if for some reason you can't save the data set? If you need to get it from, because you know how sometimes you'll find on some websites this data set, it's literally just a list of numbers separated by commas, but it's a URL, you can't save it to CSV.
Can you read in from a URL? So I think you can. I don't know that off the top of my head. I'm almost positive you can. I'm going to write that down, and if we have extra time, we'll figure it out, or I'll show it to you guys tomorrow. Okay. Any other questions? Otherwise, you can see, so we read in, this is going to be, we'll talk about the gambling data set in a minute, so don't worry too much about what these values mean, but I've read in the gambling data set from the first subject. And we're printing out the first, go away, scroller. We're printing out the first 5 rows of that data frame, and that's what we're seeing here. Okay. The other thing I should say is that if you wanted to save this, there's a lot of attributes for saving data frames out once you have them in Python. So, for example, I'm going to type df, which is our new data frame, right? Because we stored it in the variable df. I'm going to do df.to_. I'm going to do the tab completion. There are all of these functions for saving out data frames into whatever file type you might need. So there's lots and lots and lots and lots and lots of different options. So if you want them out into CSVs, you've got that. If you want them out into Excel, you've got that. If you want it to HTML, into JSON, into SQL, into Stata. That's one of the really beautiful things about the Pandas library is that it plays nice with whoever your collaborators might be and whatever file format they might need. It's really easy for you to read it in, save it back out in a way that other people can use.
Do you know how quickly those get updated, like the new release of Stata?
Oh, that's a great question.
Problematic.
The Pandas guys are really usually pretty up to speed with stuff. I can't exactly give you an estimate, but I know they're releasing, they'll release Pandas version 20.2, it's usually every once a month, every other month. It's pretty fast. A lot of these packages for the first time ever are actually getting independent grants to just further develop these packages. There's a lot of interest in making Python the universal language. So NumPy today actually just received its very first external grant. So the answer is hopefully yes. Okay, so we read in a data frame. Let's actually just go through examples of some procedures you might actually do to clean up some data that you might get. The first thing is, I don't know about you guys, a lot of these variables are kind of weird. Let's get rid of them because we actually aren't going to need most of them for the sorts of statistics we're going to be doing, because we're going to be doing some really basic statistics today. So, like I said before, the drop attribute is how you're going to drop out columns from your, or rows, in fact, from your data frame. So here I'm naming all of the variables I want to drop out. I'm storing them in a list. I'm passing it to df.drop, and the axis here specifies whether or not you want to drop from the rows or you want to drop from the columns. So axis 1 means I want to do it across the second dimension, which is our columns. And when I print that out, a lot of that messy stuff went away, and then we have a very simple data frame. So that's drop. What if we wanted to add new columns? I'm going to say right now, this is a gambling experiment, and what we're actually looking at is participants who completed this experiment basically were assigned, let's show you, basically had to do a bunch of things that looked like this. Great, that actually shows up. They were offered a bunch of 50-50 gambles. So they might have been offered, you can win $25, 50% chance, or you can lose $5, 50% chance. Do you want to accept this gamble, or do you want to reject this gamble? maybe you can get a gamble where you can win $10 and potentially lose $20. Would you accept that gamble? I most certainly would not. And maybe there's a harder case where there's a potential 50% chance of winning $25 and losing $20. I don't know about you guys, I don't know what I would do on that case. Yeah, you would? Oh, okay, cool.
Statistically, it's correct for us.
This is true, but Kahneman and Tversky, man, prospect theory. But these are the sorts of very simple experiments that psychologists and neuroscientists love studying. So if this is what helps you get up in the morning, then I totally recommend neuroscience. I haven't spent 5 years doing things like this. But that's what this data set is like. So participants completed a whole bunch of these trials, in fact, over 200 of them, while they were inside a giant magnet. And we, well, not me personally, but us fellow neuroscientists, looked at people's brains as they had to make these sort of weird decisions versus easy decisions like definite, I'm going to take it because that's definitely a win, versus definite loss versus maybe win, maybe loss. So one variable that might be useful for us here is to take the gain minus loss, right? Maybe it's that differential between whether or not you're going to win versus whether or not what you could win versus what you could lose is actually useful. And maybe I want that as a new variable in my data frame. So to do that, I'm going to index into my data frame, and I'm indexing by the gain variable, and I'm going to subtract from it the values from my loss variable. And I'm going to store that in a new variable called diff, for the difference. And when we print that out, you can see we get this brand new variable in our data frame, which is just the difference between all the gains and all the losses. So easy way of creating new variables in your data frame from pre-existing variables. We can also rename columns. If you're like me and you really, really hate writing out response time, which is frequently in my life, maybe you want to shorten that to RT. So you can use the rename attribute. So you can give it a list of columns that you would want to rename. The columns are stored in dictionary format. So here's what it's currently named as. Here's what we want to rename it to. And great, it updates. And now you don't have to spend minutes of your day typing out reaction time. I might be griping about my lab life a little bit. Again, what if we want to do different indexing? So for example, maybe what we want to do is, I don't know if you've noticed this, but we've got some -1s in our response category. I should also explain more about this data set. We've got two variables here, response number and response category. When people had to make a choice about whether or not they want to reject it or accept the gamble, they were given 4 options, 1 through 4. 1 was, I definitely want to reject this. 2, or was it the other way around? We'll get there. Well, one of the extremes was definitely want to reject, kind of want to reject, kind of want to accept, and definitely want to accept. That's what response number is here. Response category is just the binarized version of that. So it's 0 if they definitely reject, regardless of whether or not they were temperate or definite, and 1 is if they wanted to accept it. You'll notice that we have some response categories -1. That happens when a participant just didn't respond for that trial. Maybe they were sleeping because it's a scanner, or maybe they just got distracted. So maybe we want to remove all of the -1s because they don't give us any data, right? The subject didn't do anything in those trials. So we can look in our variable response category. We can use the same operator that we learned yesterday, the not equal to. So what we're saying here, find all of the rows in the matrix or in the data frame where the variable response category does not equal to -1. We're going to index into that, and we're just going to get rid of those rows. So you can see we no longer have any response categories that are -1. So that's one way of dropping data. There's some other ways we can do that. For example, we saw yesterday the numpy where command. Remember that numpy where replaces the which command from R. So we can do the same syntax. We can say, okay, every time there's a -1 in response category, return NaN, and otherwise return to me whatever that value was. And I'm going to use that to update response category. So every time it's a -1, it's now going to be a numpy NaN. And so you can see now I've got NaNs, and I can use the drop NA, which will look across all of my data, and it's going to drop any row where there's an NaN. Be super careful about that, because maybe you only want to drop NaNs from based off of sorted columns, but not other columns. We'll talk about how to address that in a minute. But this is one option you can do. In a lot of classic psychology experiments, if they don't make a response, the entire trial is useless, and I don't want to keep any of that information anyways. Okay, so there's some other useful attributes that data frames have that we can talk about it. So if you wanted to transpose your data frame and make all of your indices become your columns and all of your columns your indices, you can use transpose. Let's say you're reading in a data set where you think you might have a lot of duplicate rows. Drop duplicates will just drop all that for you. It'll find every row that's identical to itself and just return one row. And like I said before, there's fill NA, which you can also apply to data frames, just like you can apply them to series. That's one way to just categorically across the board replace all data. But again, you can't do anything fancy like specific imputations with that. Of course, you should be able to sort your data frame. So here we're going to sort our data frame by gain. Notice that it maintains the index here when we're sorting, right? So this was originally trial 2. It's supplanted where the 0 index was. So this was actually originally our 3rd trial. So it's maintaining that index. You can also, for example, yes, please.
If you ever wanted to change the index, how do you do that?
We will get there in just a second. Yeah, it's a good question. The other thing is, of course, is that with sort values, you should be limited to only sorting across one column. You should be able to sort across multiple columns. So here we're sorting by gains and losses, and I've set ascending is equal to false, so largest values down. You can actually give this a string, a list of different booleans. So if you wanted one to be ascending and the other to be descending, it can handle that, no problem. Again, we have the describe command. So I showed you describe before, where you got summary values for a series. Now you can get summary values across your entire data frame, if for whatever reason that's helpful for you. And the same thing is true with value counts. We can do value counts across a variable, and it'll, again, just be like a very simple table telling me what were all the unique values of the response number and how many times did it appear in this data set. The other nice thing is that there is the apply attribute. The apply attribute is very similar to apply in R. So let's say we wanted to apply a new function that is not already available as an attribute, like the standard score or the z-score. Just like we went through yesterday when we did it with NumPy apply across axis, we can do the same exact thing, but now we're just going to use the apply attribute from a data frame. So we're going to give it the function we just defined, the z-score, and we're going to say that axis equal to 0. We're going to apply it across our columns, and now you can see our columns have been z-scored. And the other way to check that, it's going to look funky for a second because I actually have been running a lot of this as I go along, so some things aren't updated. To just confirm that everything worked, if we do basically what you're seeing is that a lot of these columns now are effectively 0. They're like, which is exactly what a z-score should do, is the mean of a variable that's been z-scored should be 0, right? Because what you're doing is you're transforming that variable to have mean 0, standard deviation 1. And we can also confirm that by looking at the standard deviation. They're all 1s. Okay. Let's talk about how to combine different data frames together, because we're going to have to do that in just a minute, because there's lots of subjects in this experiment. There's not just one. One thing that you can do is you can add a series to a data frame. To do that, you're going to use the append attribute from the data frame, and you're going to pass it the series, and you're going to ignore the indices. That's just going to add the series as a new row all the way at the bottom of the data frame. It's going to try to match up the index from the series to the columns of the data frame. If they don't match up, you're going to get a column that's full of NaNs, because it's not going to try to delete anything, or it's not going to ignore anything. It's going to just basically give you a new column based off of the index from the series in your data frame that's just entirely missing data except for the value from the series. Did that make sense? Was that not a clear explanation? If it was not a clear explanation, let's visually show that. I like puzzling nods. Like, definitely tell me if it does not make sense. So I'm going to make a new series object that's going to have some of the attributes. So I'm going to do just 5 1s. It doesn't really matter. And I'm going to give it a few indexes that are present in our data frame. So we have gain and we have loss, but we don't have the column named random. Right? So I've got a new series objects here, and I'm going to do df.append. I'm going to append the series as the last row. I'm going to do ignore index, and I'm going to show you the last few rows. What's not defined? Oh, right. Oh, really? Might have just been making up and I've been leading you guys astray. Because I'm the worst. Maybe the new, oh. Okay. Change that thought. They've changed pandas between version Python 2 and Python 3. I should also explain that I'm also new to Python 3 because this class made me switch from Python 2 to Python 3 because I was a straggler. That's no longer a thing you're allowed to do in pandas. That's really cool. Your series actually has to match up to your data frame. So never mind, the case that I described doesn't happen because they're smarter than I am. Good for them. You can also append dictionaries to a data frame, and it's just going to do the same sort of matching that series are. Don't I look foolish now? Okay. Another way to merge data frames is with the concatenate command. So again, I'm going to import this new command from pandas. Pandas import concat. The concatenate command is how you're going to join data frames on their rows, not on their columns, but on their rows. It's not merge. We'll get to merge in a second. So if I want to just stack two data frames on top of each other, I could use concatenate. Here, this is a case where what I was saying before actually makes sense. So here we're concatenating our original data frame with a version of the data frame that only has its first three columns. So this is an incomplete data frame. It's only going to have gain, loss, and response number. And you can see when we concatenate them, then it fills in NANs at the end of the data frame where the second data frame that we added to the first one didn't have all the information that the first one did. It just filled in all of those columns with NANs. Does that make more sense? Yeah, okay. Second try. The other thing, so this shows you what I just, oh, no, sorry, never getting to merge. Merge is just like merge, it's called merge in R, if memory serves. It's the same exact thing. So to give you an example, we're going to take our data frame with its 6 variables. We're going to split it into 2 different data frames. The first data frame is going to have gain, loss, response number, and response category. The second data frame is going to have gain, loss, reaction time, and the difference. As you can see, we've got 2 different data frames now. We're going to merge. The syntax for merge is very similar to the syntax for R. So we're doing data frame 1.merge. We're passing it the second data frame we want to merge it with. We're telling it which variables we want it to merge on. So we're going to have it merge on gain and loss, because gain and loss are both present in our 2 mini data frames. And you can specify how you want it to merge, and this is the same exact features as it is in R. So you can do inner merge, where if certain values in one data frame don't match up to the second data frame, it throws away that data. You can do outer, where it completes everything, where you just get a lot of NANs. You can set it so that it respects all the values in the first data frame, but not the second, or vice versa, where it respects all the values in the second data frame and not the first. That's similar to the merge syntax with R. Are people familiar with the merge syntax in R? Yeah? Okay. So this should be pretty familiar to everybody then. It's remarkably similar. In fact, it's identical because they made it as such. The other thing you can do is you can merge on indices. As opposed to merging on columns, you just specify that you want to merge on the left index and the right index of these 2 data frames. And you can see, because gain and loss were both present as columns in data frame 1 and data frame 2, it didn't merge them together, it just duplicated them. So now we have gain x and loss x, which is from the first data frame, and gain y and loss y, which is from the second data frame, because it didn't want to get rid of them because we were specifying to merge on the index. Also similar to how R does it. Does that make sense to everybody? That's combining data frames, which can be really, really important. Okay. We're, from here on out, going to start moving in to much more exciting data use actual cases. We're going to actually start showing real scripts, and we're going to start moving into visualization, and we're going to start moving into statistics. This was sort of a crash course in using data frames in Python. Before we start moving forward, are there any functions, for example, that you wanted to see from R that you don't know if exist in Python? Or did that material make sense and you are waiting to just see the cool stuff? Take that as people are excited to move on. Okay. This is just explaining the data set. Here's an actual case of a more realistic script you could write in Python. So the data set that we have here is 16 human subjects. They played this gambling task 3 different times for a total of 256 trials for every subject, meaning that we have 3 times 16 files, meaning we have 48 files that we need to merge together and do a little bit of pre-processing on, because we want to remove all of the trials where they didn't make a response, and we also want to drop the column, the variables that aren't interesting to us, and we're going to want to rename some columns. So literally, this script here is everything that we just went through before. It's every single step, it's just put into one longer Python script. So let's explain just briefly what it's doing. This is a list comprehension that just like we had yesterday. And what I'm doing is I'm going to introduce this new command to you guys, the os.lister. OS is that module or that library that we imported before. Lister just means list the directory. I'm listing all the files in the gambling directory. And I'm specifying that I only want the files that begin with subject, which is how I named all of my files. Like it's a subject file that starts with subject, makes sense. And just return all of those files in a list. I'm going to make an empty list here to just give you the high-level overview of what this giant for loop is going to do. It's going to read in every subject's data file. It's going to do some pre-processing. It's going to store it in this list, and at the end, we're going to use the concat or concatenate command to join them all together so that we have one data frame that represents all the data from all of our participants in one data structure. So does that make sense? So here we're just taking our file name and just finding out what subject and what run it was. We're using retable like we just did to read in the data. We're doing dropping of the columns just like I showed you before to get rid of the variables we don't want. I'm removing all the missing data just like I showed you before by taking all the places where the response category variable doesn't equal to -1, and I'm using that to index into the data frame to just return the rows. Yes?
There's like a dplyr equivalent.
There are, so in terms
Finding data wrangling, piping it all together.
There are equivalents. That is definitely a place where it's lacking. There is a little bit more potentially scripting involved here. That is a place where Python or Pandas might be inferior to R. There probably are, but they're not as familiar to me. I can look that up for you if you want, though. So we're renaming the columns, we're computing that diff variable, and here we are with concatenate, we're storing it all together. I'm just sorting my values, and here's the first 5 rows from this actually really, really long. You can see this is the shape of our data frame up top. It's nearly 4,000 rows and it's 8 variables. So it's actually a decently large, I mean, not huge, but large enough. I'm also right here going to just reorder our columns. I'd like to know at the leftmost like what subject it came from and what version of that task they were playing. So to do that, I'm just indexing all the columns. There are better ways to do this if you want to, into the data and just updating data so that it's now sorted by column the way that I've specified here. The other thing, going back to one of the questions that were asked before, is that we now see that our index is sort of out of order. Let's reset that index. We can do that just with reset index, and we can set it all back through 0 through the number of rows. Okay. And if we want to save it, here's an example of using toCSV. So I'm actually saving out all the group data into a new CSV file, not a tab-separated file, or you can save it as a tab-separated file using the sep flag, just like in R. So we're saving out as the group gambling data, and that's in your folder. Okay. Questions about that? Or is that pretty clear? Yeah. Okay. One thing to point out is that data frames can do categorical data, just like R can do categorical data. There's the info attribute, which will actually tell you how all the different columns in your data frame are being represented. So we've got 2 object variables, which are just strings. We've got a lot of integers, because most of our values are just single integer values. And we've got 1 float, which makes sense. It's our reaction time data, which is continuous. If you wanted to make your data frame more lightweight in memory, we could store all the subject names and all the run names, which are right now strings. It's literally subject 1, subject 2. We could store those as categories where under the hood, it's going to represent all those things as integers and not as strings. So you have to represent fewer pieces of information in memory. And you can see our original matrix was 250 kilobytes, which is nothing, but we can get it down to 80% of that and take off about 50 kilobytes. Not very impressive here, really impressive if you're trying to use data frames to work with text data and you want to actually like dramatically scale down the amount of space that your data frames need in memory, which also can dramatically improve efficiency of doing operations over your data frame. So just be aware of that. Okay. We're going to start moving to things like pivot tables. Let's actually start computing some actual summary statistics from our data. Pivot tables and the like are called group by objects in pandas. We're going to take our data frame, which is now the data, or it's variable named data. We're going to use the .groupBy attribute, and we're going to tell it what variable we want to group on. So here we're just going to group across all of our subjects. So all the rows of our data that belong to a given subject are now ready to be grouped across. In general, in pandas, there's 3 different types of operations you can do with group by objects. There's aggregation methods, which are basically just computing summary statistics over your groups. So for example, if we wanted to find all of the average responses, binarized responses, and all the average reaction times across all of our subjects, we could use the .mean attribute on this new group by variable. And you can see this is a new group by variable. It's represented as a group by variable, or a group by class. We can do .mean, specifying on these 2 variables that we're interested in, response category and reaction time, and it'll print out this lovely little table for us saying the average of those variables for all of our subjects. So it's averaging across all the rows of that data frame. You can also do group bys across multiple variables. So here we're doing a group by on the response category across gain and loss. So here you can start seeing it's going to print out this long list. It's going to shorten it at some point, just showing what the average number of takes were across all of our subjects for a given gain value and for a given loss value. You've noticed so far I'm mostly using .mean because .mean is an attribute that's already stored in a data frame object. Let's say that your value is not, or like let's say your function that you want to use to summarize the data is not already an attribute, like the percentile function. You can use the groupby.aggregate attribute to specify the function across which you want to summarize your data. That makes sense to everybody? So here, I'm going to specify the groupby object.aggregate. I'm going to specify the NumPy percentile function that we saw yesterday. I'm going to pass in the additional flag, which is required by percentile, which is just what percentile do you actually want to see. So this is for the 70th percentile. And it will compute out, for all of our variables, because I didn't specify otherwise, what the 70th percentile of that variable was, splitting by the gain and loss attributes. So that's one way of doing aggregation of your data. And that's a long list. Does that make sense, everybody? Okay. Another thing you might want to do, one final thing I should say about once you make a group by object, like a group by table, you can index into it with the .loc attribute, just like we saw before, and you just want to specify what variables you want to index into it. So here we're specifying by the 30 gain and the 15 loss, and we can get those values out. There's also a pivot table function, which it basically accomplishes the same exact thing. The syntax is a little different. You're going to tell it what you want on your index, what you want in your columns, what values you want represented, and how you want to aggregate it, which is, I think, a little bit more similar to how R does it. And it'll spit out this lovely little table, which is actually just, again, just another NumPy matrix with a little, with just column and row information stored across it. So you could save out this pivot table, for example, into a CSV or into anything that you want if you wanted to save that and send it off to collaborators. Another thing that you could do with group by objects is to transform them. So let's say that you want to specifically do, transformation is really useful, for example, for imputations. So let's say instead of using fill in A, which just does it blindly, so it's going to fill in A regardless of maybe something interesting about particular classes of a variable. So for example, in this case, if you want to do imputation on reaction times, you don't want to just impute, if you're going to do a very simple imputation, you don't want to impute into that subject what the average reaction time was across the group, because some people are just in general really slow and some people in general are just really fast. You want to impute the average reaction time for that subject into the missing data for that subject. Did that make sense? Okay, so you can use that with the transform attribute. So here, what I did was just briefly, I made a new data frame called missing data, where I just put some missing data for a few subjects in there, where they're missing data on their reaction times. The transform syntax, for the first time, is using the lambda operator. We briefly went over the lambda operator yesterday. I said this is exactly what it'd be used for, and this is exactly what it's going to be used for. So good job, Pat Sam. So the transform attribute, or what you're basically going to be doing is, whatever you group by, and we're grouping by subject, you're going to say, where there is missing data for that subject, perform the following operation. So wherever there is missing data, because we're going to use fill and A, put into that the average value for that variable. I know that's complicated. So just to say it one more time. For X, which here is going to represent columns of your data frame, because it's going to iterate over the columns of your data frame, it's going to pass X from the lambda, and it's going to take the average value for that column, and it's going to pass that into fill and A. So here you're specifically passing the average reaction time for a subject into their response times, so that you're imputing by participant.
For missing values for the column vectors, or?
Yeah, for the missing values across the columns.
Okay.
Yeah. Does that make sense? Okay. Finally, there's filtration. So let's say you wanted to reduce your data set down by certain specific attributes. So let's say you wanted to only look at subjects who on average had, so here the response category means whether or not they took a gamble or not. So let's say you only want to look at the subjects who took gambles more than 50% of the time. You can use the filter attribute. So it's the same exact thing as before. So we're passing in across all the columns. So for the column response category, if the average value for that subject was greater than 0.5, return a new data frame that only contains those subjects for whom that conditional was met. And so you can see before we had 16 subjects, we now only have, 7 subjects. So we only kept the 7 subjects who took the gamble over 50% of the time. Does that make sense? Okay. All right. Those are some things you can do with data frames. That's some of the syntax. Let's start moving into visualization. This is going to go a little bit faster, and I'll spend a little bit less time explaining the syntax of those functions. There's going to be 2 libraries we're going to be covering today. The MATLAB plotting library, otherwise shortened as matplotlib, which basically recreates all of the MATLAB plotting functions. This is sort of the core visualization library. To give you the summary off the top, it's a little clunky, which is why right after we get through some basic examples with Matplotlib, we're going to introduce Seaborn, which plays really, really nicely with Pandas data frames, as long as your data frame is essentially stored in a long list format, which will cut down on the amount of code you need to write to make pretty graphs dramatically. So just know that off the top. So it's actually, Seaborn is sort of like the ggplot of Python. Here we're just going to import Matplotlib. There's a lot of different backends to Matplotlib. You don't have to worry about that too much, but basically for general plotting, you just want to use the PyPlot sub-module of Matplotlib. We could talk about that if you care. The other thing I'm doing is that I'm using a little bit of Jupyter Magic here, which is actually what it's called. I'm not even kidding. It's called Jupyter Magic commands. That's what this % means right here. What I'm saying is I want all the plots to be plotted inside the notebook. I don't want it to make a new window. That's how you can make some of these things kind of prettier. The core most important thing in terms of jargon for MATLAB is just similar to, or for Python, or the recreation thereof, is that there's sort of 2 things. There's the figure, and then there are axes. The axes are the individual plots that are made inside of a figure. In general, if you're making a plot, there's only going to be 1 axe per figure. You're going to only have 1 histogram for the entire plot that you're making, but let's say you want to make multiple plots. You want to have a bar plot and histogram and scatter plot side by side. That means you're going to have 3 axes inside 1 figure. And that becomes important because in terms of the commands that you're going to be calling, Matplotlib makes a pretty strong distinction between axes and figures. So just to show you the basic syntax, we're opening a new figure here. So we're doing plt.figure, so now we have a new canvas on which to plot. We're opening up a new axe. What this value here means is that inside our figure is going to have 1 row, 1 column, and we're opening up the first plot, or the first axe of that figure. We're going to do some things here. We're just going to make a bar plot, so we're just going to average across our data. This is all group by objects that we've seen before. This is the very clunky number of lines of code for doing even simple bar plots with matplotlib. This is all going to get replaced very soon. But we actually have the plotting command right here. You have to specify where you want the bar plots to start, which is the left. You want to specify how tall the bar plot should be, which is the height, how wide you want them to be, and you can specify color if you want. That's going to create a new axe. And from there, we are going to set a bunch of attributes on this thing, meaning that we're going to change the different features of it. So with plotting in R, this core plotting, all of those things are inside the original function, so you can change the color and the X label and the Y label and the X text and the Y text inside the function. You do that through axe with matplotlib. So you can see I have plotted the bar plots here, but now I'm making a bunch of flourishes to my plot. So I'm changing the X limits and the ticks and the tick labels and all those things. Basic plot, yes.
And color and width be variables, can they be dynamic?
Yep, so you can actually give lists. So you can make certain bars wider, you can make certain bars different colors. It's all going to get much easier, but so you would have to sort of manually specify all that though. And to really drive home how kind of obnoxious that is in core matplotlib, you need a lot of code, for example, to just make a grouped bar plot. It's also not a very aesthetically pleasing group bar plot. But matplotlib has all the basic plots, so again, we're going to do the same exact code. The only thing that's changing now is I'm using x.plot instead of x.bar to make a line plot. I'm also going to use the x.fillBetween to add some confidence intervals along our line. So again, it's a lot of code to produce that. All this is going to get replaced. Scatter plots, x.scatter. You specify what's going to be on the X, what's going to be on the Y. You specify the size of your markers, what marker shape you want it to be, the color of your markers. Again, you specify a bunch of the X and Y details, and you can get a scatter plot. Okay. Histograms, same exact thing, obviously one-dimensional. Done a little fancier here. I've set a legend, for example, to show the difference between these two subjects. Made that call right here. And we can go through more detailed, but just to sort of start going through things. The other thing is that there's an alpha parameter here so that these things are transparent, so you can actually see between them. So alpha is the transparency function of these plots. I know I'm going through this quickly. It's because you can, if you want to, you can really go through these examples and really pick them apart. A lot of them will get replaced once we have Seaborn. We can definitely talk about more of it if you guys are interested. But matplotlib also can do heat maps. This has to be some of the most kind of obnoxious syntax, and I will say this. You specify your two-dimensional matrix that you want to be represented as a heat map. Specify what aspect you want. I'm going to let matplotlib just automatically rescale it for me. Don't want to interpolate it. I don't want to apply any smoothing onto my data. I want it to start from the bottom corner. I want to give it a color map. We can give some color map examples later, and what the upper and lower limits of my color map are going to be. And okay, so it's at least kind of pretty, but it's a lot of code to do these things. Really briefly, just to explain the difference between figures and axes, I just want to show that there's ways in Python, just like in R, to embed multiple axes or multiple plots inside one figure. There's a number of ways to do this. So for example, we can use the subplot command. The subplot command is a really simple syntax. You just tell it how many rows you want your figure to be, how many columns you want your figure to be, so how many plots per row, how many plots per column, and which plot of that figure you want to start editing. Did that make sense? So in this first line here, what I'm saying is, in general, my figure is going to have 2 rows and 2 columns. That's the first 2. And I want to edit the first plot of what's going to be my 4-plot figure, so my top left corner. And I can repeat that all the way down, and you can get something that looks like this. So I can plot top left, top right, bottom left, bottom right. So you can do multiple plots in one figure. Another way to do this is with subplots, which instead of having to multiply call all of these individual commands, will just return all of the axes in just one list, so that you can, for example, just do a for loop across them, and that way just recreate the same figure with fewer lines of code. So here's just a for loop, a very simple for loop. I'm doing all the same things that I did above. I've just condensed it down by passing the axis I want to plot along. Does that make sense? There's also the subplot to grid. which is a little bit more confusing in the syntax. Again, the first thing here says how many rows and how many plots of my figure. This one says specifically with the indices which axis I want to work on. So 0, 0 means I want the top left corner of my now 3x3 figure. And col span and row span are going to be the new variables. That says I actually want to merge all of the axes across the top row. If that doesn't make sense, maybe it makes a little bit more sense now. You can see by setting col span 3, when I initialized this first plot up top, what I said was join what would have been the first one and the second one and the third one into one large horizontal axis. You can do the same thing to do it vertically, and the syntax is just changing from col span to row span to make it vertical, because you're collapsing across rows. It's all hideous, I know. It's going to get easier, I promise. Grid spec is probably the nastiest. If you want to do custom plots with custom spacing and dividing up figures in every which way, you can use grid spec. I'm not going to go through it in detail. Just know that you can do really complex figures where you could embed multiple figures inside figures and have arbitrary spacings between figures and create any sort of mishmash. It's all there for you to use if you want to use it. I'm going to skip over them, if that's okay with everybody. Pandas, I should also just briefly say, have some very basic plotting functions. If you just want to like quickly look at your data, you can take the data frame or group by object and just use the plot functions from it, and you can specify what sort of plot you want to make. So you can very quickly make bar plots that aren't especially aesthetically pleasing, or very quickly make line plots that aren't especially aesthetically pleasing. You can do it very quickly though, so that's a very like one-line way of making plots if you just want to quickly look at your data. Okay. Seaborn is really what we should spend a little bit more time on. It's basically trying to be the ggplot of R. This is their documents page. There is a ton of content to Seaborn. We're going to only scratch the surface tonight, but there's tons and tons of different sorts of plots you can make and visualize your data in all sorts of different ways. The real take-home message is if your data frame is in long list, meaning that you're melting your data frame so that which we'll go through plenty of examples of. So that doesn't initially make sense right now. You'll know what this means by the end of the workshop. Once you have your data in long list, Seaborn will make lots and tons of pretty plots for you without a lot of lines of code. Let's take the same data set we've been working with, and actually show this. We're going to import the Seaborn library. I'm going to use the shorthand of the SNS because I don't want to type Seaborn every time. Two important things we're going to set in the back end is that we're going to set the set style, which basically changes sort of the color preferences of your plots. So you have a few options. You have white, which means it's just a pure white background. You have white grid if you want to automatically have a white background and have grid lines on your plot. There's dark if you want to have a brooding sort of plot. And there's also dark grid, so you can have a darker color scheme plus grid lines. There's also the set context. Set context is just wonderful because if you noticed above, a lot of my function calls, I'm sorry if I'm giving anybody whiplash, a lot of my function calls was just setting the font size of a lot of different labels and ticks and things like that. Once I get back down, oh man, that would have been a good time to show you guys navigate. The set context is really nice because you can tell it what sort of plots you're trying to make. So for example, you can specify, oh, I'm trying to plot in a notebook, or I'm actually trying to make figures for a paper, or I'm trying to make figures for a talk, or I'm trying to make figures for a poster. And it will use a set of default parameters that scale your plots that are actually usually at least good default parameters to make nice plots for different contexts. And the other thing is you can set a font scale so that you don't have to spend a lot of time actually changing the fonts of your plots. You could just say, okay, I'm just going to double what the default is, and that way you guys will be able to see it. And here's just a very basic plot. You can see it already starting to begin, it's a little bit crisper, but let's actually start showing. Remember before I needed about like 20 lines of code to get a bar plot? Now I need 2, which is much nicer, and you get a lot of things that come for free, like nicer colors. You can remove the edges. You can what's known as de-spine, so I can remove the top and right edges from your plots if you want them to be a little less constrained. It will automatically compute error bars for me. There's lots and lots and lots of different ways to customize this, to do different sort of aggregation techniques. If you want standard error versus standard deviation versus whatever. But the point is 2 lines of code. All you have to do is just give it your data frame, and you specifically just need to specify which variable is going to be on your x-axis, which variable is going to be on your y-axis, which data frame you're passing, and maybe a few other function calls if you want. So I specified a color here, because otherwise it would default to giving me a rainbow bar plot. Same thing for line plots. There's a lot of code before. It's now 2 lines of code, and that's only because I was being a little neurotic. You could actually, its defaults are totally fine. But again, on the on the x, I want that difference variable that we made. On the x, why am I getting these backwards? On the x, I want the difference variable. On the y, I want the response number. I just give it a variable. Instead of plotting all the individual points from our data, of which there are many, I'm just saying, hey, bin the data by the difference variable. And it will automatically make this plot for me. It'll automatically compute a trend line for me. And it will automatically show the average of my data points with the error bars. Yep.
So it looks like basically first you draw the figure, like how big you want it, and then each X thing like draws on the figure basically.
That's
so,
exactly right.
Kind of like with ggplot, you can name a variable and everything is just like, if you call that variable, the plot will show up. Like, is there something like that with? I don't know if I'm.
No, I don't think so. So it's a slight difference, yeah. Actually, you could just, I should take that back. You could just call this thing and give it the data, and it will automatically plot that without actually opening the figure. It will actually automatically plot that for you, if that's what you mean. I'm doing specific scales here because I'm working in the context of a notebook, and I want it to be not taking up a huge amount of space. Does that answer your question? Or, so what I'm saying is with Seaborn now, you actually technically don't even need this line of code. This line of code can disappear, and you could just run this, and it will actually make a new plot for you. It'll make a new figure, a new canvas for you. I don't know if that's what you meant, though.
I guess I was just saying, like, let's say I call it like whatever, X, right? I want to call a plot X, and if I just want to write, like, literally type X, and the plot will show up wherever I want. Like, can I do that, or do I have to do that code every time?
I think you might have to do this, yeah.
All right.
There, again, you could write wrappers and there might be some piping stuff. I really should look into some piping stuff.
Yeah, I think she means, can you assign a plot to an object?
Basically,
Yes.
yeah.
Oh, yes. No. Yes.
Yeah.
Absolutely, you can.
Okay.
Yes. Sorry, if that's all you mean. There was like no immediate function that I could think of that would like automatically do all that for you. But yes.
Because it looks like a separate lines of code that like when all like put together like creates a plot versus just like I don't know.
You could. Yes, you could set some defaults. For example, one thing I'm not showing you is there's lots of ways to set defaults with Seaborn, so you could just call this line of code and then this would be generated. You just have to do a little initialization ahead of time so that you tell it what sorts of things you're looking for, and that's what you mean. We can also talk about it if I'm not addressing your question.
Okay.
Yeah. More examples, again, just plots with very little amount of code. Same thing here. You want to do scatter plots, things like that. You can also automatically generate the same sorts of multiple figures like I said before. So you can, for example, call facet grid, which will make that same sort of multiple figure per canvas, or multiple plot per canvas figure. And you can just pass it, it'll make a wrapper function, G, and you just pass it whatever plotting function you want. It'll automatically apply that for a given data set. So I'm passing it our data set. I'm saying on the columns, I want it to be our subject. I'm saying for every 4 subjects, make a new row. Saying that they should share the same x ticks and y ticks. Otherwise, what I'm saying here is on the y plot, or sorry, on the x plot the reaction time and do some other functions that get applied to histograms. But 2 lines of code generates many, many figures. Key map, same thing, nice defaults. Just 1 line of code in this case can just go ahead and make all this all at once. So this, like I said, the real takeaway with all this is once your data is in a data frame, you can do away with a lot of the sort of nasty old things with Matplotlib and actually start making really nice plots. And there are just tons and tons of tutorials, and we will start showing those as we start moving through the workshop. Finally, for tonight, we're going to just do some brief overviews with stats models. Stats models is sort of the basic LME4-like or LM-like statistics package or statistics library that is trying to make itself similar to a lot of the statistics functions in R. So Again, I've linked to the documentation here. Before we do that, I'm just going to show a few basic functions in SciPy. For the sake of time, just know that SciPy has a lot of additional functions. So for example, SciPy, for example, if you want just the core probability distributions for lots of different probability distributions, like the normal distribution, the gamma distribution, the inverse gamma distribution, the Weinbold distribution, whatever you want, SciPy has it programmed. So if you need to either fit data based off of different distributions or generate data from different distributions, SciPy has that. They also have additional functions for computing like the skew of your data, and they also have some very basic statistics functions. So you can do Pearson correlation, non-parametric correlations, one-way ANOVA, t-tests, chi-square analyses. I'm going to come back to this at the end to show you guys some interactive examples. This is just showing, for example, if you wanted to do a QQ plot, so if you wanted to see whether or not your data was normally distributed, or whether or not it's have skew, just one line of code, you can get, the kurtosis plot. Everybody's familiar with that. Yeah. Just a quick test to see whether or not your data is normally distributed or whether or not you have heavy tails on one side or both sides. Same thing as before I was talking about. You can import from SciPy, which we'll talk a little bit more about later. From SciPy.stats, we can take out, for example, the Pearson R correlation coefficient, a one sample or two sample t-test, or one-way ANOVA. I've generated some random data just to show you that basically you could just pass in matrices and you can compute t-tests. So if you need quick t-values or f-values and p-values for those things, SciPy's got you covered. Do you guys want me to go through that in detail, or is that enough for those basic things? Okay. Let's actually get into stats models. Stats models is, again, going to be like the formula-like package, similar to what R does to fit either ordinary least squares models or mixed effects models or full GLM. And it actually has a lot of additional things if you want to do time series analysis. There's a lot of stuff in there. Like, I guess I wrote it down. Like generalized estimating the questions or weighted least squares. So stats models got a lot programmed. Doesn't have everything that LME4 has, which is why I'm going to show you how to call LME4 from Python at the end of this. But let's at least show you stats models. So for example, if we wanted to fit an ordinary least squares model to some of the data that we had before, so for example, if we wanted to predict what effect the gain and loss values from our gambling task has on what people chose, we can just define the same formula that you would normally use in R. We can use this OLS class. We can do dot from formula, pass it the formula, pass it our data, fit the model, and you can easily compute a summary table. This is just like you would have in R, right? So it gives you a bunch of summary statistics about the fit of the model, and then it actually gives you the coefficients and the t-values and the p-values for that model. I'm assuming everybody's familiar with using that stuff in R. So stats models recreates a lot of that. This is just to show you that diff actually is a more parsimonious fit, but sure. We have mixed effects models. One major limitation of stats models is that they currently only have linear mixed effects models. So if you want to run more complicated mixed effects GLM, stats models does not currently have that. I can show you just a version of at least the linear mixed effects models. So we're going to import from stats models this mixed LM or mixed linear model. Again, same formula from before. We're passing in our data. And as opposed to the normal syntax that you would see in R, if you want to do, for example, a random intercept model where you would have parentheses, one division, like subjects. Does that make sense? Does everybody's familiar with that syntax with fitting formulas in R? Yeah? If not, we can also go through that after. That's replaced with the mixed effects with just the groups. So you just explicitly tell it what you want the groups by. And you can give it different functions in here, whether or not you want it to be. It will always assume the default is to do random intercepts, but if you want to do random slopes, you just specify it in a slightly different way. You could look at the doctrine and it'll tell you. And here's our random effects. Do logistic regression with the logit. So we're going to import from statsmodels.api. We have the response category variable, which is the binarized version of the response class. Same exact thing. You just define what the formula is, pass it in. Great. Got a logistic regression as well. You can do ANOVA with the same exact syntax as is used in R. So you can use, like in the same way you can do ANOVA with LM in R, you can do the same thing with stats models. So I'm defining a few variables as categorical here. So response number is now a categorical variable. And stats models, if you pass it a data frame where one of your variables is categorical, it will treat it as such and will set up all the demi-coded variables necessary for computing an ANOVA. So it'll do that for you automatically, so you don't necessarily have to go through and make demi-coded variables with from a data frame, although I should say that if you want to do that easily, there is a function from pandas where you can do from pandas import, what is it, get dummies? Yeah. Where if you give it a categorical variable, it will return the dummy-coded versions for each of those variables. So if you have 4 variables, one column will represent the first variable, it'll just be ones and zeros. Second will represent the second variable, or second instance of that variable. And we can do basic GLM. So for example, here, reaction times are oftentimes better fitted as a gamma distribution because they have heavy right tails than a linear model. So again, GLM, same exact things before. Here I'm making an assumption that reaction times are parabolically distributed, which they actually are when it comes to your point of indifference in decision making, but that doesn't really matter here. Point is that it's the same exact syntax that you've seen from R. We can give it a formula, pass it the formula, pass it the data frame. Here I'm only fitting it to one subject, so I'm saying, okay, I only fit it to a subset of this data. This is just a conditional saying return true, where every one of those variables is our subject 1. That's an easy way to just subset it. Okay, that was a super crash course, but that's mostly just because stats models is really just trying to replace the same functions that LM and LME4 have in R. So, and I'm assuming that's been drilled into you guys. If not, we can do that after class, but I'm assuming you're all familiar with that. So you got a lot of the basic functionality. Like I said before, stats models is newer as a package and doesn't completely have all of the functions that LME4 has. So for example, there's a lot of things from its GLM that has not been made yet. So one thing that I can show you is, very quickly, I'll give you a brief demonstration. It is actually really easy, especially now with Jupyter Notebooks, to call R from Python. So if you were going through a series of calculations and you realized that stats models didn't have something that you needed, it's not a problem. If you run this command, and I've actually tested this on both Mac and Windows today, I'm almost positive it should hopefully work for everybody. That's why we sent out that PowerPoint earlier. You can run the following 4 things, and you can actually now run an LME4 model in Python. So first, we're going to load as an extension in the notebook this rpy2 library. It's just a library that allows you to make function calls from Python to R. And just to give you an example of this, I'm doing the same sort of notebook magic now. The double % R means that everything in this cell should be interpreted as R code and not as Python code. So that's why seek works. Seek is not a Python command, obviously it's an R command, and it's actually running now. So, yes?
And installing, loading libraries.
It's in the, so the other thing I should say, so we sent out an email before the class that has installation instructions for Anaconda, uninstall and uninstallation instructions for Anaconda if you're just so turned off by Python after this, but also additional installs for, I'm so sorry about yesterday, we figured it out, very specific instructions now for updating packages on both Mac and Windows, for doing, joining the R library with your Anaconda distribution for both Mac and Windows. It's all documented, as well as documenting how to install some of the extensions. Sorry about that technical hiccup yesterday, but I tested it both on multiple laptops today. Where I ran into problems, I specifically found the solutions to those problems. If you guys run into issues, please definitely let me know if the PowerPoints don't work for you, because my guess is that it's probably not going to work for at least a fraction of you guys, and I want all these installs to be actually working for everybody.
So just to clarify, we were to run install packages.
It's not going to work right now unless you need to follow.
Okay, but once you do all the proper installing and updating, is that still how you would call it?
This part?
No.
I'm sorry.
So if you wanted to use a dplyr function
Yes,
through R.
I will explain that in just a second, because this was just to show you that it's possible. Here's how you would actually do that. Okay. So the syntax for calling a library that you might want, so here we're just calling the LME4 library, is to do this $R and require, because now we're going to say whatever R sessions that are running in the background of this notebook now, load in the following library. So you could load in dplyr, or you could load in LME4. Here's what you would do. Oh yes, you had a question.
For the require code, do you know how in R Markdown that require only works for that chunk? Does that only work for that cell?
No. As you'll see, here I'm actually going to run an LME4 function, the glmr function. So I called it here, but I'm actually calling it in this next cell now. So it's actually for the entire notebook now. So you can open it all the way at the top of your notebook, and down here you can call it and it'll be fine. But to pass data frames in, all you need is just this -i flag, meaning that you're passing a variable from Python, a variable currently instantiated in Python, like data, which is our data frame in Python. We're going to pass that in so that it can now be read from our R code. So -i data, I'm passing data into R, and this is just the glmr function, right? So I'm giving it the same formula that we used before, telling it data, and I'm going to do, in this case, I'm doing a mixed effects gamma model, because that's actually the best way to fit. It's actually not the best way, but it's the second best way to fit reaction time data. It's actually not even close, but that doesn't matter. The point is that I've actually been able to run this model now, and you can see it actually fit, and now you get the outputs that you were used to from R. So it is possible. You actually don't really need to make a compromise anymore. The other thing that I learned today, going back to that starting PowerPoint, there are also, oh, get out of here. All right, fine, don't get out of here. So are libraries now that can make function calls to Python as well, which I actually didn't know. So if you want some functions from Python, but you still want to program in R, you can do both. So hopefully, one way or another. Oh, commercial. Why not both? That's a reference for 4 of you. Okay. You had a question?
Yes. The difference between 1% sign and 2 before the R?
This is making backend calls for the R library. So for example, this is starting R. This is for loading R packages into the R installation. This just basically says that I actually want to execute R code. So if I tried executing R code in the cell, it wouldn't work. I'd have to put in the double percentage signs. It's a little bit of an annoying syntax. It has more to do with the Jupyter Magic stuff, which we can actually go through a tutorial on if you want.
And the semicolon?
That was because I was actually trying to suppress this annoying warning message, which just says that we've loaded in both the matrix library and the other one. I actually have to figure out how to suppress those messages. But that's an artifact of Sam's failures. So, but no.
You used them before and they worked fine. So.
Yeah, no, so they worked for Python for sure. So there's clearly specific things I need to do for R. That second half was a bit of a breeze through. I focused more, oh, that's it for tonight, I should say. We are at end. The first half was obviously very series and data frame heavy. That's because I really want you guys to feel comfortable with the syntax of using series of data frames. Once you feel comfortable doing that, you can really start breezing through doing very basic stuff, or even more complex stuff. And again, the main lesson I sort of want you guys to take away is that once your data is in a Pandas data frame, stats models plays nicely with it, Seaborn plays nicely with it, so at least basic statistics and basic visualization all happens like that now. Very few lines of code, right? Similar to R, just how R is very lightweight in terms of very quickly fitting statistical models. And the other reason why that's important, as we'll come back to on Thursday, is because once your data is in a Pandas library, when we start moving into machine learning, the machine learning library we're going to be using plays very nicely with the Pandas data frame, so it starts becoming even easier to start fitting complex machine learning models with very few lines of code. So everything up at the top that looks really clunky and has many, many lines of code, that really starts disappearing very quickly once your code is nicely formatted. You can do a whole lot with very little with Python. So, yeah. And just like yesterday, there's also exercises. If you want to do the exercises, if anybody is doing the exercises and you're liking them, let me know. If you're not liking them, also let me know. And like I said,